then, so we got this chapter, and what we'll do is we'll finish off this. We might not finish it off today, but we'll get close. And then we have, so next time is catch up, and then we have the test. So we have today, we have the class today, we have catch up on Wednesday, and then following Monday is the test. So I'm hoping that on the Wednesday we'll finish relatively early, and then we can, you know, you can ask me questions and stuff like that. Bring questions for me. Okay, so let's see if my pen's up and running. Yeah, okay. So we're going to talk in terms of DC circuits, and we've got to start being able to analyze simple circuits, and the most common architectural feature is the distinction between a series bit and a parallel bit. And maybe I can define it best by saying that when there is a parallel bit, there's some kind of junction in the wires. When there's a series bit, there isn't. Now, in truth, you will get combinations of series bits and parallel bits put in together. So they'll be different. They'll be all messed in together. So you've got to recognize little bits. But the telltale is not how they're positioned on the page, but how they, what happens structurally. If I go to the bottom, I can maybe illustrate this by saying, you know, here's a circuit. There's a circuit element, and if I have resistor A, resistor B, and resistor C, and that looks like it's got a parallel bit, B and C are in parallel with each other, and then that is in series with A. So you do this, you're going to go, okay. And this is the combination of B combined with C. So you could think of it as, well, there's a series bit, which is the combination of B and C in series with A. But the unambiguous bit is the B is parallel to C, yeah? But I can draw this circuit just the same way by going like this. That is the same circuit. And it's just, it doesn't look anything like it. So and the trick is, look, oh look, there's a junction there and a junction there. So that's the first skill, is can you spot the parallel bits from the series bits? If you can, then you can go to the next stage, which is how do we calculate the equivalent resistance? Why do we need to do this? Because resistors come in certain sizes, and you might want a combined resistance which is different from that certain size. Secondly, this might in fact be not a resistor, but a component that has resistance. And so these could be light bulbs. And we're doing them in series for a certain reason, or we're doing them in parallel for a certain reason. Classically, if you have a whole bunch of lights strung together in series, they'll work. But what will happen is that if one of them breaks, they'll all stop glowing, and you won't know which one is broken. And that was in, you know, holiday time. You know, people would take out the lights, and one of them wouldn't work, and then none of them would work. And you'd have to replace each light in turn until, if by chance you found the one that was broken. And, you know, hope there's not two broken, because, you know, 2 out of 13 is a tremendous number of permutations and combinations. So people started moving from that design for the lights to this design where they're in parallel with each other, where one burns out, the other 12 keep on working. So, okay. Various reasons why we want to be able to analyze series and combination bits, and we're going to think about just pure resistors to begin with. It's a bit of a useless circuit. It's like it's only just playing with potential differences for the sake of playing with potential differences. We did something similar with capacitors, and you may have learned the rules for capacitors, in which case just flip the rules. I can intuitively justify these rules by saying, imagine that a resistor is a straw, and imagine that the narrowness of the straw determines the resistance, and the length of the straw determines the resistance. So this is like having a straw connected to a straw by a huge big pipe. So here's the big pipe. And it goes round here to some kind of pump. So you have, you know, water flowing, and then it gets this straw and it gets resisted. Goes through this bit, no resistance. Gets to this bit, gets resisted. And you can see that it has to work its way through the first resistor, then it has to work its way through the second resistor. So if I said to you, can you make one that replaces these two? You'd have a straw which is, you know, longer and, you know. So it makes sense that in series, you add the resistors arithmetically, you know. And that the equivalent resistance is bigger than either one of these two guys. Whereas when you added capacitors in series, you were increasing the gap, which was reducing the electric field, which was reducing the capacitance. Now, when we add these things in series, we're increasing the resistance. Okay. And, you know, I can point out to you the fact that if I have a straw, it's got a certain resistance. If I put another straw around it, if I put another straw around it, if I put another straw around it, that's like having a big fat straw, or a short fat straw. And there's less resistance. Blowing through a short wide straw is a lot less than blowing through 4 long narrow straws. So it makes sense that the resistance decreases in parallel, and so 1 over R equivalent equals 1 over R1 plus 1 over R2, etc. Yeah. So that's the hand waving argument of justifying these. And yes, question.
Back to the slide, please. So what if you add another resistor?
Oh, and so I'm sorry. These should have dot dot dots. So this would be R3 and R4, and this should be 1 over R3 plus 1 over R4, and 5 and 6 and 7.
Okay. If you add another resistor that acts diagonally.
Oh, I'm sorry. Add another resistor. Where am I on the page?
Series or parallel?
This guy?
Yeah.
If I have add another resistor where?
I think you need to decombine the series.
Like diagonally.
He's talking about series parallel, sir.
Yeah.
Okay, draw another.
Do you mean like there?
From the bottom of the switch to the top.
Yeah, it's right there.
There?
There?
And go diagonally.
Oh, yeah.
All the way up. Correct.
Like that?
Find an equivalent.
Oh, so that is, if I can draw it here, there's my power supply. Think of these wires as being bits of elastic. You can just move them and stretch them and change their shape. So I'm going to simply take that point there and say that's a junction, and that point there, and that's a junction, yeah? Because they're junctions, yeah? There's 3 wires coming together. There's 3 wires coming together, so that's a junction. That's a junction over here. That's a junction. Yeah? So then I simply have lost my pen. So then I simply come along here, and I can do it like this. I can do junction. Junction. And then on this side, on that side, I have that guy. And on that guy side, I have that and that. So those are in series, and then these are in parallel. Let's get a page and let's play with this, because it's useful. It's a fair question. It's a useful thing to think about. So let's the thing was, it was, oh, don't even go there, cancel. So boom. So we had this, didn't we? So let's label this X and Y. Yeah. So I'm going to go along here. I'm going to go, oh look, that's that bit of wire there, and then that bit of wire I've drawn like that. So this is X and this is Y. And then I can take this wire and just stretch it out. I can take that wire and stretch it out. And then I take, well, that bit of wire goes from there to there. And then this bit of wire goes from there to there. So if I have A, B, and C, I have A, B, and C. Now, In principle, there's no reason to change your diagram, but I find this analysis hard. I find this one hard to analyze because it's not nice and set. I prefer to have this guy looking like this. It just is clearer to me. That's just three. I'm going to contrast these two. Both of them contain series and parallel bits. I can say this is A and that's B and that's C, yeah, whatever. Doesn't matter. There's no significance in the letters, just so we can identify. The way I'd attack this one is I would say these two need to be combined first. And my justification for that is that they are unambiguously in parallel. If I try to solve these two, the A and B first, well, hold on. What about A and C? Isn't A and C just like A and B? And which one should I do first? And all that kind of stuff. You know, I mean, it's like, but I can recognize, oh, this is unambiguously in parallel. And then what I can do is I can say, well, okay, now I'm going to take this combination, the B-C combination, and it's in series with A, and I'll do that bit second. It's a bit like eating spaghetti. It's like, where do you begin? Okay. But on this guy, it's not the parallel bit that's unambiguous. It's the series bit that's unambiguous. So I would then get this to that. And this would be A. And this would be my BC combination. And then I'd solve that next. So there's nothing special about parallel first and then series. It's not that way at all. It's just you think of the bit that's unambiguous first, and then you do the other bit. So let me do a really complicated example. So what I do on this is, well, let's label them. Let's go A, B, C, D, E, and F. I want the equivalent resistance. You're going to bring that down to one equivalent resistor. So somebody tell me, where are you going to start? D and E, because they're clearly in series, yeah? And so then I go, well, that goes to, my pen's not so good, but I have that, I know, I can't be bothered. So now what do I do? B, C, and then this is D and E, yeah? So I do that bit next. Sari, be quiet. And then I do that bit next. And I don't know of a way I can tell you that. Just, you know, there's no rule I can give you. You just look for the unambiguous bit, and then you do that. Then you say, what have I got? And you do the next unambiguous bit. Yeah. And then the other thing that's worth playing with is just getting used to this old idea that, let's say I give you this. This is a question that could come up. So can you draw that in a more standard form for me, please?
That one is just a parallel series. Yeah.
That's just like the same series we had before, but with B cut off.
So again, that's a junction. So form the junction and then do that across. And then on this side, there's two of them. And that's a junction. And on this side, there's only one. And then this guy comes down here. Yeah. And there's a certain skill in that. And you don't often get things drawn like this, but I've seen it. And certainly I've seen it on tests. AP likes to do stuff like that. Yeah. So play with it. It's a low-grade skill, but if you've not practiced it, it'll flummox you, you know. It's not, you don't have to be Albert Einstein to do this, but if you've not practiced it, you probably won't be able to do it on a test, you know. So, okay. An 8 ohm resistor is connected in series with a 4 ohm resistor. What is the equivalent resistance of this resistor network? Can you do that one for me, please? I'm going to just pause. So basically we have an 8 ohm resistor in series with a 4 ohm resistor, and we say R series equals R1 plus R2 plus ... and we just put our numbers in and we get 12 ohms. Can you ever go to this next one, please? This is a, well, we'll do it together. So an 8 ohm resistor is connected in parallel, so and so this is 8 ohm and this is 4 ohm. 1 over Rp is equal to 1 over R1 plus 1 over R2 ... So 1 over Rp is equal to 1 over 8 plus 1 over 4. Common base is 8. So 1 over 8 plus 2 over 8, which is 3 over 8. And I can't tell you how many people will give me that as the answer. Rp is equal to 8 over 3, which equals 2.66 ohms, which is there. And that's, again, that's not writing your equation down. That mistake of giving me the 3 over 8 is not writing your equation down or not writing in complete sentences once you get to that stage. So it's you know, it's a mistake that's highly correctable. This next one, unfortunately, I'm sorry, I did this one time and I recorded it, and it's burned into the file now. So what I'm going to do is, let's have a look. It's a 3, an 8, and a 2. And what I'll do is I'll just go to this next page and we'll do it together. So we have 3. Doesn't matter which way around these guys are. We'll do it like that. So this is 3 ohms, 8 ohms, and 2 ohms. So what we do is we say, okay, this is unambiguously in parallel, so I'm going to say 1 over Rp is equal to 1 over R1 plus 1 over R2. So 1 over Rp is equal to 1 over 8 plus 1 over 2. 1 over Rp is equal to 1 over 8 plus, multiply both sides, top and bottom, by 4. 4 over 8, which equals 5 over 8. So Rp is equal to 8 over 5. I'm going to leave it like that, actually. And then I come along here and I go, well, this is 3 ohms, and this is 8 over 5 ohms, and this is 3 ohms. So I say R series is equal to R1 plus R2. So R series is equal to 3 plus 8 over 5. R series is equal to, multiply top and bottom by 5, so that's 15 over 5 plus 8 over 5, which equals 23 over 5. So our series is equal to 4.6, I think is the right answer. So bomb. Okay. And then the next little wrinkle is, that's just finding the equivalent. Let's start looking at voltages and currents. And I got to tell you that this is a little bit, it's a little bit more involved than, it's called simple circuits, but in fact it's not quite so simple. So this says a 12 volt EMF is applied. So let's draw a circuit out. So here's my battery. And that's 12 volts. And then this is 4 ohms, and this is 2 ohms, this is 6 ohms. And now it's asking what specifically is the current flow through the 2 ohm resistor. So it's asking for the current flow through that bit of wire, and only that bit of wire. So now we've got to visualize a bit better than we've been doing. So it wants I, and I'm going to, for the sake of shorthand, call it I2. Now, in a little while, I'm going to introduce you to another type of analysis, and this nomenclature is not so good for that. So I'm going to, it's within context. When in this kind of problem, in simple circuits, when I say I2, I mean the current through the 2 ohm resistor. When I say V2, I mean the voltage drop across the 2 ohm resistor, and so on. It's a way of just keeping track. And I'm talking about this piece of wire here. So now let's do the equivalent. So this is like a pump. And then let's actually just, well, we'll think about it in the same old way. Here's a big, huge water pipe. And then we have a couple of little bits. And then the big, huge water pipe connects these guys together again. And then there's another little bit. And then the big, huge water pipe takes all the water back. So can you see how the big, huge water pipes we don't care so much about? It doesn't matter. The pieces of wire we don't care so much about. But I want the current flowing through this part. So I want the amount of water per second flowing through here. So this is my I2 is through there. Okay. And it's not obvious. You know V equals IR, and you know R series equals R1 plus R2, and you know 1 over RP equals 1 over R1 plus R1 over R2. So it's not about the math. It's about picking away at it. And so what you learn is, well, your first tool in your toolbox is Ohm's law. So I'm going to say, let's try and solve it in one step. And I'm going to say I2 is equal to V2 over R2, which equals V2 over 2. Because I know that R2 is 2. Yep. But I don't know what V2 is. So let's do another step. And now my V2 is here. That's my V2. It's my potential difference across the 2 ohm resistor. And it's tempting to say, oh, well, V2 equals I2. V2 equals I2 times R2. But that's the equation I just used. So I'm going in a circle. That's not going to get me anywhere. So although that's a correct equation, it is trivial because it doesn't help me.
So why, excuse me.
Yep.
So why then V is not the same as 12?
Oh, good question. So if this is think of it as water pressure. If there's 12 psi of water pressure there, and this is a nice fat pipe, then there's 12 psi of water pressure there and 12 psi of water pressure there, yeah? And if there's 0 psi of water pressure there, there's no pounds per square inch of water pressure there, then there's no pounds of water pressure there. But that's not the bottom of this straw. That's the bottom of the system. So the voltage drop across here is 12 volts, but not across this one particular device. Yeah? It's like height. It's like if I have a step ladder that is 12 meters high, and then I say, well, hold on, I can get to the same height by having 2 little step ladders stuck on a balcony, and then another step ladder going there. If that's 12 meters, it's not 12 meters there, is it? It's 12 meters from the very top to the very bottom. So, yeah, the voltage drop across here, voltage drop across that one component is not the same as the voltage drop across the whole system. Cool. But now you do raise an issue here, which is, I know that my total EMF, my total voltage produced is my EMF, is equal to the voltage drop across the top component, which is the 2, added to the voltage drop across the bottom component, which is the 6. So I know that. That's interesting. So let's substitute in. So 12 is equal to the voltage drop across the 2 plus the voltage drop across the 6. So then let's turn around and say, okay, voltage drop across the 2 is equal to the 12 minus the voltage drop across the 6. Because it's that I need to find. Again, I don't know V6. V6 is the voltage drop across here. Well, let's go back to Ohm's law. The voltage drop across the 6 is equal to the current flow through the 6 times the resistance of the 6, which equals 6 times I6. But I don't know I6. Oh, I6, by the way, is that. I6, yeah? And then this is, again, you wouldn't necessarily think of it unless you practice this a bit, but I have, I system. What comes into or goes out of the battery. I6 is the same as I system. What comes into or comes out of the battery. I system is equal to V system over R system. And V system, well, that's just your EMF over R system, which equals 12 over R system. Ooh. So next, I have to find my R system. I'm going to go through it and then we'll step through it again. So I'm looking here. And the unambiguous bit, let's change the colour of my pen. So the unambiguous bit is that bit. 1 over Rp is equal to 1 over R1 plus 1 over R2, which equals 1 over 4 plus 1 over 2, which equals 1 over 4 plus 2 over 4, which equals 3 over 4. So Rp is equal to 4 over 3. And then we do the series bit. Series is equal to, let's redraw it just so we know it. This is 4 over 3 ohms, and this here is 6 ohms. So I say, well, R3 equals R1, R series is R1 plus R2, which equals 4 over 3 plus 6, which equals 4 over 3 plus 18 over 3, which equals 22 over 3, which equals 7.33 ohms. I'm going to change colour pens because I'm going to go into another bit. So now I come along and I go, well, this equals 12 over 7.33, which equals 2. And I think it's just, you don't have to do your calculations as you go, but I think it's just easier to follow what I'm doing if I do the calculations as I go. So this equals 1.64 amps. So that means that this equals 1.64 amps, which means that this is 6 times 1.64 which equals times 6 equals 9.82 volts, which means that this equals 12 minus 9.82. 12 minus second answer is equal to 2 point, which equals 2.18 volts. So now we come up here and we take that up here, and that equals 2.18 over 2, which equals 1.09 amps. Now, none of those steps in themselves are hard, but the problem is it's not obvious what the next step is, I think, when you first begin doing these. And my advice is you want to work your way into a simpler and simpler circuit. So I know I'm at the end when I'm talking about I system and R system and V system. I know, oh, that's as far out as I can go. But I can't just like jump there because I won't have the pattern. So my secondary piece of advice is try and solve it in one step, and that's usually using V equals IR. And then if you've used V equals IR and it did not give you the answer, then you got to look at the next bit, and you're either going to recognize that these currents add together because it's a parallel bit, or these voltages add together because it's a series bit. And with this, having done V equals IR, let's change my colour pen again so we can just not, we don't forget. So in colour, let's do this in black so we see. So having done V equals IR on that bit, and it didn't get me the answer, I recognize, oh, well, that is in series with that, so I can use some of my voltages on that bit. And then I try and use my voltage to get I try and use V equals IR to get my voltage. And so can you see I'm kind of stepping. This is a V equals IR bit. And that's a V equals IR bit. And there's some of the and that's a V equals IR bit. It's like every second time it's a V equals IR bit, and every other time I'm either recognizing a pattern of the voltages or I'm recognizing a pattern of the currents. Can you see that? So I'm doing V equals IR, that didn't work. Oh, I'm going to use a voltage bit. Now I'm going to use V equals IR. Oh, that didn't work, so now I'm going to use, and it could be a voltage bit, it could be a current bit. So I'm stepping through like that. And that's the kind of navigation through this. This is important because this tends not to be answered well. And I want to do another one, but I want to do one of the complementary ones. So I'm going to do, let's do 12 volts. Let's make it simple. 2 ohms, 4 ohms, and let's do 2 ohms. Let's make this one 6 ohms. Okay, and let's say this is 12 volts. So there's my circuit. And I want to know the current flow through the 2 ohm resistor. So I want to find I2. Okay. So I'm looking down here, and I go I is equal to V over R. So my current flowing through my 2 is my potential difference across my 2 over the resistance of my 2, which is V2 over 2. But I don't know what my V2 is. I know that it's not 12 volts. So then I say, oh, well, okay. And now there's a whole bunch of ways I can go. I can say, okay, then my voltage across the 2 is equal to my EMF minus my voltage across the 4. I got to start thinking now, because some lead me up blind alleys. So voltage across the 4. So if I work out my voltage across the 4, that's not going to take me anywhere, you see. Because if I have my voltage across the 2 and have my EMF and my voltage across the 4, I've got to find my voltage across the 4. Finding my voltage across the 4 is just as hard as finding my voltage across the 2. I've not gone anywhere. I've not progressed. It's a correct statement, but I've not progressed. So that's not a good way to go. So is there another way I can find my voltage? In fact, is there another way I can find this all together? You've got two guys got their hands up, so I'm messing up. What? What do you think?
I was gonna ask if we can't just for the time being, treat the 2 and the 4 as a single 6 ohm resistor, and then separate the voltage coming into that.
So yes, you can combine them and play with it that way. I want to actually, I'm making it's a bit of hard work about this, but this is how I'm going to do it. I'm going to find the current flow coming out of my circuit, I system, and I'm going to find the current flow down this guy, I6, and then I'm going to subtract those two and find my current flow down my 2. Okay, so I really would like to start by trying to solve it from one step, and I'm going to say my current flow through my 2 plus my current flow through my 6 is equal to my current flow down my system.
I2, you mean I2 plus I?
Well, the same current flows through those guys. So my current flow down this side plus my current flow down that side equals my current flow out of my system. Yes.
Can I derail you with that?
Okay.
Just one step, right?
You know that in a parallel circuit, the voltage drop is going to be across both branches, so it's just going to be, you're going to deal with 12 volts and then those 2 resistors.
Brilliant. So
You didn't add another resistor, so.
So another way of analyzing these guys is to say, hold on. So what we do is we say, okay, look at this. My current flow here, let's call it I is equal to I2. Does that make sense? The current flow through this little resistor is the same as the current flowing into this arm. Yeah? And the current flowing into the arm, I, is equal to the, let's put it arm, A-R-M. A-R-M. I-arm is equal to V-arm over times over R-arm. So it's this bit here. So I turn around and I say, oh, I-arm is equal to V arm, which is 12, because it's just across. The 12 volts is there, and the 12 volts is there, over R arm. And I'm going to be real specific about this. R arm is equal to R1 plus R2, which equals to 4 plus 2, which equals 6, because R series is equal to R arm. It's a series combination, yeah? Oh, so I arm is equal to 12 over 6, which equals 2 amps. So therefore, I2 is equal to 2 amps. So what do you feel about that?
And you can, yeah, that's probably the easier way. You can do it the long way too. There's other ways to solve the problem.
And that's the this is kind of like the dilemma we have when we're teaching this, is that it's called simple circuits because when you get it, it's long, but it is simple. The equations are simple. It's conceptual understanding. It's knowing the current splits at a junction, the potential differences add in a series bit. It's knowing those concepts, which for us are brand new, but for people, you'll eventually practice them. And then it's just 2 simple equations or 3 simple equations. It's not that it's mathematically hard, but it's not, because in a way there's 5 different ways of solving these things, and some of them are quicker than others. They can be very long, tedious problems, or with a little bit of insight, they can be quite short. And so the dilemma is, I've got to try and make it so that you won't give up on them. And so what I tend to do is I tend to limit the circuit configurations. And my methodology is, I want you to practice these several configurations. And then, yeah, guess what's going to happen? You're going to turn around at some point and you're going to get the pattern, and then you can do more complicated ones. But if I don't kind of reward you for trying this limited family, then you're not going to make that step where you go to the more complicated stuff. So the patterns that I stick to are like this. I would give you a circuit which is like that, which is the same as like that, which is the same as those 3 are the same, yeah. That's a series with a parallel. And the other one I do is basically, I'm going to show it like that, which is that. So it's the parallel with a series bit inside. Those are the, and again, and I can draw that like by saying it's that, and then it's that and that, those 2 are the same. So those are the 2 configurations that the question will come from. And it's worth points. So, and I could ask you for the voltage drop across. I could ask you for the current through. So that's the game I'm going to play. I'm not going to do anything outside that family. Okay. And then my sense is that if you can do those 2, when you see something more complicated, with a bit of thinking, you can get the other one. I'm going to stop there, and I was hoping to get further, but we didn't. But it's okay.